Hello, this is Professor Dan Kernler of Elgin Community College. This is another video in my statistics series. This one is about hypothesis testing, this time about standard deviations and variances. All right, let's get to it. So far in this series, we've done two different hypothesis tests. We've done one comparing proportions and then another comparing means. So logically, the next one would be variance or standard deviation. Let's remind ourselves the steps to the hypothesis testing process. First thing we need to do is define the null and alternative hypotheses. Then we want a level of significance. We'll compute a test statistic, and we're going to need a new one this time. We want to compute the p-value or the critical value, make a decision, and then state a conclusion. So for this test, we actually have a couple of options. When we look at our null hypothesis, it could be about a variance, that the variance is equal to a specific variance value, or there's this relationship between the variance and standard deviation, and you could have a null hypothesis about the standard deviation. For the alternative, now we're talking about spread. So if we look at, say, our random variable, we say it's going to be distributed this way. Our null hypothesis is that the variance is equal to whatever this variance is from the null hypothesis. We might wonder, hey, is it maybe less spread out? So then the alternative would be that the variance is less than that null variance. Or we could say, hey, maybe we think it's more spread out, so then the variance would be more than the null hypothesis. Or maybe we just don't know, so then we put a not equal to. Sorry, President Obama. So we really have three options here. Even more if you look at them in terms of standard deviation, but we could have a less than, a greater than, or a not equal to. Now for the test statistic, you're going to recognize this one from the confidence interval. It's a chi-squared. We have n-1 s squared over the variance, in this case the variance from the null hypothesis. This is really important that this distribution is only true if the x, the original variable, is normally distributed. So that is a strict criteria here. We have to check that the original variable is normally distributed. And then you have the other three steps in the process as usual. Let's look at an example. I looked up one in our education data. I'll put the link in the description below. But we have this average kindergarten class size. If you look at it across the state, pretty bell-shaped symmetric distribution, it's reasonable to say that's approximately normal. What if we look at one district, say school district U46? It's in the Elgin area. That's where the college is based. So a lot of school district U46 students come to Elgin Community College. And you would suspect well, since it's just one district, there's probably less variability. The class sizes in the elementary schools are probably relatively similar because they're all in the same district. So we might make this claim: is the variance of the average class size for kindergarten classes in school district U46 less than that of kindergarten classes statewide? Right? Again, because it's one district, there probably is less variability. In fact, here's the histogram. You can see the difference in the population and sample standard deviation, and certainly the histogram looks more condensed. So it seems reasonable, but we'll need to check to see if that sample standard deviation is significant enough to end up being statistically significant. Let's go through that hypothesis testing process. First thing, we need a null hypothesis. We're going to assume that the standard deviation is the same as the population until proven otherwise. That's the null hypothesis. For our alternative, well, here's the distribution shape with this standard deviation. That's the assumption from the null hypothesis. We think ours is going to be less spread out. We think there's going to be less variability. So we think our alternative is that the standard deviation is less than 5.62. That's going to be our alternative. Let's use the usual alpha for level of significance, 0.05. The test statistic, it's just chi-squared n-1 s squared over sigma from the null hypothesis squared. Let's do this in StatCrunch. This one is a little funky in StatCrunch because we just want to select school district U46. So we'll do stat, variance stats, one sample from data, and we'll scroll down and find average class size, just kindergarten, and then we need to choose just school district U46. So what we do is under the where box, we type district equals, and since it's not just one word, StatCrunch doesn't like spaces, so we need to quote SD space U-46 and then end quotes. So we have to put the quotes around it if there's a space or a symbol. StatCrunch isn't smart enough otherwise. We have our variance. Now you got to be careful. StatCrunch is always doing hypothesis tests about variance. So we need to make sure we put in 5.62 squared. And you can actually just type that into StatCrunch. And then we're going to do less than for our alternative hypothesis. Hit compute. and then we have our results. So we have our chi-squared test statistic 13.04, the p-value less than 0.0001. For the critical value, we're going to need a chi-squared. We're going to need a chi-squared that has 0.05 to its left. We're going to need to go back into StatCrunch and use the chi-squared calculator. Now let's grab the degrees of freedom from the previous output. That's 39. So then we'll go stat, calculators, chi-square. Looks like chi-square, but it's pronounced chi-square. We have degrees of freedom is 39. We want the area to the left, and we want 0.05 to be that area. And then we get our critical value. So let's put our critical value into the process. To help you visualize this, here's the chi-square distribution shape with a degree of freedom of 39. And our 25.7 is over on the left, and there's area of 0.05 to the left. It's a left-tailed test, so our critical region is going to be on the left. Okay, back to our decision. Well, let's look at our test statistic and our p-value. The p-value is less than 0.0001, so we should reject. And if we look at our test statistic, it's over there in the rejection region, 13.04. So then we make our decision. It's to reject the null hypothesis. So then our conclusion is that there is enough evidence at the 0.05 level of significance to support the claim that the variance for average class sizes in kindergarten for school district U46 is less than that of kindergarten classes statewide. All right, that is it for this video. Kind of a short one, but the hypothesis testing process starts to become repetitive, and you really hopefully can get in a rhythm for it. You just have to have a new, what are the null, what are the alternative, a new test statistic, but then the process becomes the same. You compare your p-value or critical value, you make a decision, you state a conclusion. So hope you enjoyed this. Hope you found this helpful. If you're interested in seeing more of these, you can subscribe, hit the bell to get notified. We have several more hypothesis test videos coming out. As always, thank you to the Elgin Community College Board of Trustees for approving my sabbatical during the spring 2021 semester. That's the only way I would have ever had enough time to do all of this recording and editing and producing all of these videos. Thank you so much for watching, and I'll see you in the next one.